It's
All
not
right.
here with us.
I mean, there's nothing on there. I can tell you. It's just a school iPad. All right.
We gotta have a reset
334.4 joules. I got for one. 334.4 joules. That's what I got for number one. Raise your hand if you got that. 5, 6 people. The rest of you know. All right, we're gonna go over it.
And we kept it. Oh my God.
Okay, so that's number one. Is that endo or exo? Number one. How do we know?
Endo.
How do we know? It's positive. Positive Q, positive delta H. They're basically the same thing. That tells me it's endothermic. Here's the other way you can tell. Number one says water is heated. If I heat water, I'm giving it energy. So the water temperature goes up because it's gaining energy. That's endo, absorbing energy. All right, 6. We'll do that last. 7. 7 was tricky because you do use Q equals MC delta T, but you don't use the 4.18. You look down the back here, and on the back it has aluminum specific heat, which is 0.899. So the answer to 7, again, I'll show you the work here, but 7 is 539.4. 539.4 joules, 539.4 joules. And that again is endothermic because it's heated. It's gaining energy. It's positive. Temperature goes up. That's what that second line is. So you see the line next to delta H, that's your answer. Underneath it, I want you to write endo or exo. That's what I want you to write. Said it on top, but I think some of you just went right to the prompts. Okay, so let me go through 1 and 7, like showing you how I did that, and then we'll do 6. Okay, so number 1, you're using Q equals MC delta T. Q is what we're looking for. What's the mass of the water? Jenny?
40 grams.
40 grams, good. Jake, what's specific heat of water again?
4.18.
Good, 4.18. And the delta T, Zach, what's that for number 1?
20.
20, good job. And it's positive 20 because it's final minus initial. 30 minus 10. So you multiply all three and you get whatever I just said, 334.4 joules. And that is how much energy the water gains when it increases 20 degrees. Okay, number 7. Q equals again. The mass of aluminum is 30. The specific heat was 0.899. And who can tell me what's the delta T for number 7? How about Kayla?
20.
20 again. Good. And the answer was 539.4 joules. Is that right?
I don't think so.
That doesn't seem right to me.
I got like 3,000. I got the
Yeah, am I missing a number?
No, you just.
No, I got like 3. I got the same number,
3,000.
so I got 3,000.
Oh, so
Yeah.
that doesn't go there.
Yeah.
That makes way more sense. My fault.
I thought I just put the dot in the wrong.
No, I did it wrong. I wrote it down wrong.
Okay.
My fault. Sorry about that. Here's why. Obviously, I'm a chemistry teacher, so I can pick up on things. But here's what I want you to understand. You should look at those two numbers. This number should not be smaller than that. That's what I had. I had a smaller number here. That's why I knew it was wrong. You should be able to figure it out after today. Why? How come this should be bigger than that?
Because that's getting multiplied by a large.
The numbers are bigger. 40 times 4.18 times 20. Those three numbers are bigger than these three numbers. Sometimes when you're doing calculations, I don't care if it's in math or science or whatever, you should really kind of make sense of your answer. So if you're doing two similar calculations, you should kind of be somewhat aware of what you're getting, and that's how I knew I made a mistake. That couldn't be smaller. It's way bigger. That's why. Okay, we're going to talk about the demo in a second. That number is really small. Aluminum has a really small specific heat, low. Water, very high specific heat, and that's why the pot and the water in the beaker is going to be different. We'll do that. I'll kind of walk around. I want you to touch it so you can experience the science behind it. Explaining that. Explaining small versus big specific heats. So questions on 1 and 7. I'm going to go over 6. So you're going to finish this for Monday. This is homework. You're going to do the same thing. You're showing your work. You're giving me the answers. Tell me if it's endothermic, both are endo, or if it's exo, releasing heat. Okay? All right, so no questions. Here we go. Number 6. Can anyone tell me how to set this up? I told you in your notes yesterday how you know what equation to use. There's 3 of them. Q equals MC delta T, Q equals MHF, Q equals MHV. This is not a Q equals MC delta T. Someone tell me why I know reading number 6, I can't use Q equals MC delta T. Someone give me one reason why I can't use that in number 6.
There's no change in temperature.
Very good. There's no change in temperature. It says 100 degrees and that's it. You can't plug that in for delta T. That doesn't make sense. Delta means change. That means two temperatures. So you can't use it on number 6. The other reason, I'll give it to you to save a little bit of time, is when it's going through a phase change like boiling, number 6, you don't use Q equals MC delta T, you use one of the other ones. What's the other one? What's the one we use? You'd have to look it up in your notes or if you remember. Which equation? It's either Q equals MHF or Q equals MHV. Which one do we use for boiling? HV. Vaporization sounds like boiling, right? So we're using Q equals MHV. So Q is what we're solving for. Mass of water for number 6 is 40 grams. And the HV, heat of vaporization of water. Blake, what do you got? Heat of vaporization for water. It is on the back. We can use it, but I prefer to use the reference tables. That's right, we'll use the back for now. 2,257. Good. Now, I'm going to rewrite that with the units. If I have 40 grams and I multiply it by 2,257 joules per gram, what units cancel out? If I have grams times joules per gram. Grams, right? Grams cancel, so joules are left over. Sometimes I don't do that enough. That's my mistake there. I want you guys to understand the units do cancel. That's why we multiply these together. So Q equals, I have two different answers. This one, using that number, is 9280. So 90,280 joules. That's if you use 2257. If you go to the reference table, this number is 2260. Then that becomes 9,400 there. So 90,400 joules. Okay, so that's for boiling. That's when you use heat of vaporization. So that's number 6. Number 5, you're not using Q equals MC delta T. Again, that's the one weird one. All the other ones you use Q equals MC delta T. Don't forget these values are on the back here, okay? For the weird metal, the different metals and stuff, not water. All right. Questions on 1, 6, or 7? Okay, put that away. That's due Monday. Take out your notes, or actually what you wrote for the demo. And let's talk about it. And in the meantime, I'm gonna carry around some hot water. You can experience science today.
Charlie, I will brought you.
Okay, hold on spot. You got time to go?
Oh,
Yep, super hot.
way out. Wow. Zach, feel how hot the pot is. Feel it. Isn't the hot? What? Isn't the pot so hot?
Dude, hot. Experience science. Enjoy.
Hot. Hot. Not hot. Really hot.
So again, the point is, just so you guys really understand, no.
Yes, Jake, you can drink it.
Yes, it will be hot. I don't know if the back of your hand really gets it done. Okay, so if I'm holding this, that's nice and warm. If I'm holding this,
Super hot.
not so much. Okay, so the concept here, the water cooled down pretty well too, but the concept here is that the pot is made of what? What do you think it's made of? What do you think this is made of?
Titanium, copper, and gold.
Alloy, right, an alloy. It's aluminum now. It's probably aluminum alloy, maybe. Doubt it's pure aluminum, but it's aluminum. We'll call it aluminum. I erased it, 0.899. That's specific heat, so it heats up really quick. It only needs 0.9 joules to go up 1 degree. This needs 4 joules to go up 1 degree. So water, this is going to stay warm for a long time. Okay, I'll leave it on the table. It'll probably feel warm to me, to touch for the next couple hours. Okay, there's a lot of water here, and the glass is a pretty good insulator too. So anyways, this cools down very quickly. Again, the concept here, it's not super exciting demo here, but the concept, this cools down quick because it's low specific heat. It also heats up very quickly too. What else about metals allows them to heat up fast and cool down fast? What are metals good at doing? Conducting, right. They conduct heat and electricity. If any of you want to take AP Chem, we actually learn exactly why metals conduct electricity, why metals conduct heat. It's actually really confusing, even to me. I teach AP Chem. I'm supposed to be an expert, but that one topic is brand new. I've never learned it in my life, but now it's part of the curriculum. So I took a workshop last year, and they explained it a little bit. And the teacher explained it, and all the teachers taking the class were all just like me, AP Chem teachers. We all just kind of looked at each other like, what? Like we had never learned this before. So it's pretty interesting as to how this happens. It's really complex. Anyways, the easiest way to explain to you guys is that metals, particles are really close together and very compact, so that when heat is traveling, it can go from one to the other very easily. That's an easy way to explain it. There's more to it, but that's why metals conduct so well. Whereas things like water or glass, other substances aren't put together the same way as metals, so therefore they don't conduct as well. But let's talk about the two liquids now. Two liquids. Who have I now? I haven't talked to a lot of you guys. Steph, what do you think?
The right liquid had a lower specific heat.
Good. So the one on the right, boiled, had lower specific heat. Lower specific heat. That was acetone. The water on the left had a higher specific heat. And she's right on the money. Acetone was heated up faster, absorbed the heat faster, so therefore lower specific heat. Very good. Why? It is weaker. It's hard because what I just talked about with the metal might be confusing. So forget the metal for a second. If you're comparing two liquids, first of all, this should kind of ring a bell. What does that look like to you?
Rainbow.
An upside down rainbow. I guess you're right. I didn't
There was a
expect you
rainbow
to say that.
yesterday.
Can you
Saw
have
it
leprechaun
yesterday.
on it?
There was a rainbow
Yeah.
yesterday.
Okay, in chemistry class, what does that remind you of? I hope somebody.
Table H.
Yes, table. Who said that?
I did.
Good job, table H. Yeah, this is water. This is H2O. This right here, that's the boiling point of propanone. Guess what propanone is called in real life?
Propane.
Acetone. What did we learn about acetone on table H? What you just said. Devin just said it. Has a lower boiling point.
Rainbow?
No, before the rainbow comment.
Weaker forces.
It has weaker forces. Acetone has weaker forces. Let's think about this for a second. If acetone is weaker, does it make sense that it heats up faster? Yes, it does. Here's why. When temperature increases, what happens to particles in that substance? They move faster. So if they're held together very tightly, they're not going to move around very easily. So water has stronger forces. As it heats up, the particles don't move as fast as quickly because they're held together with tighter, stronger forces.
What the hell was that?
There's a fly. It was coming right at my eyeball. You guys can't see the fly. It just looks like a... Right. There's actually a fly. Swear to God, I'm not losing it. No, it's a straight up fly. It's a big fly. No, it's just a fly. Anyways, stay with me. Acetone, the particles are a little further apart. They're held looser, so when you heat it up, they can move around faster. So acetone having a weaker force means lower specific heat compared to water because the particles can move around and that increases the temperature faster. So do you need to know that for the regents? No. I just like explaining things kind of to the point of, you can't ask why anymore. I need you to understand concepts, not just memorize things, right? So don't just memorize, okay, something with a lower specific heat heats up faster. That's good, but can you explain why? That separates, right? That's people who do, get 90s on regents exams versus 70s. So that's why I teach it. It's why I explain it. So anyways, that was it. That's the point of the demo. Again, not super exciting, but the point is the one that heats up faster had the lower specific heat and it has weaker forces. So your notes should be out. So what I want to do, I'm going to give you two problems here. One here. Put them in your notes and do the best you can to solve them. If you need a calculator, they're here. It's more heat problems. So here we go. Calculate the number of joules required to melt 10 grams of ice at 0 degrees Celsius. So that's the first problem. Second problem. Calculate the number of joules.
What joules like diamonds?
Yeah, I think of that sometimes. Required to melt 10, no, not melt, I just said that. Boil. Boil 10 grams of water at 100 degrees Celsius. So I'm going to give you a few minutes here, copy it down and solve it, show your work, and then we'll go over it, and then that's going to be about it. Spell's going to rank. If we get chopped off, we'll pick up with this on Monday, but we should be able to get it in. Taylor, Monday after school. Steph, you're coming at 6 p. Shelby, you're going to show me that worksheet Monday, I would assume. She's not here. And Shelby, Taylor, and Steph, did you guys hand in that phase diagram lab thing?
If you collect, if you were like taking
Looks like this.
notes down like Monday.
That graph we made in lab.
I think so.
Sounds
I
pretty
don't
cold.
know if I
Sounds
finished it.
cool.
Alright, did you?
I
Well, you two at the end of class, get your folders out and we'll check. Okay, we're gonna go right to the bell here. You know what your homework is. Make sure you have these down. I'll have to read the answers to that quiz I handed back Monday. Obviously, I don't have time. Everyone has these written down at least? Some of you might be solving them. So, in the sake of time here, this one is melting, so we're using Q equals MHF. HF is for melting. Boiling, we use Q equals MHV, heat of vaporization. Those two numbers are on table B. Okay, if you have time, fill in or solve it. If not, we'll pick it up on Monday. Don't forget the worksheets. I apologize, we got stuck, but we had so much fun talking about pot.
Rainbow.
Pot and water here. The pot and the
do
water.
you want me to do or wait
I
till
need
Monday?
to. Is there something wrong with that pencil? Why are you throwing it out?
Do you want me to
I'll drink
You
that
don't have any
one.
time today?
No, it doesn't. Shut up.
Hey,
I bet you on like
Just because if I can explain it a little bit to you, I might be able to see that. Hey, stop that recording, will you please? Just don't knock it off.
Are you